Right now, as you read these words, the universe is growing. Every second, the space between distant galaxies stretches by thousands of miles. But here's what shatters our intuition. It's not expanding into anything. No cosmic warehouse, no outer boundary, no bigger container waiting to be filled. This isn't a limitation of our telescopes or a gap in our knowledge. It's a feature of reality that forces us to rethink what we mean by space in the first place. Picture a balloon inflating in your living room. As air flows in, the rubber pushes outward against the surrounding air. The balloon grows because there's space for it to grow into. Your living room provides that space. This makes perfect sense. This is how expansion works in daily life. But the universe runs on different rules. When cosmologists say the universe is expanding, your brain immediately summons the balloon, space stretching outward into a larger nothing. You imagine a boundary where our universe ends and something else begins. That intuition isn't just off, it's asking an impossible question. The universe isn't expanding into anything because there is no anything for it to expand into. No container, no outside. The universe creates the very concept of space as it grows. Try a different image. You're drawing a circle that's bigger than your paper, except the paper itself grows to accommodate your drawing. In our world, growth always seems to invade a pre-existing somewhere. Plants into air, cities into countryside, ice across water. We're trained to look for a destination. But what if you are the paper and the drawing simultaneously? In 1929, Edwin Hubble noticed that galaxies farther from us recede faster than nearby ones. At first glance, that feels like an explosion with us at the center. The reality is stranger. Space itself stretches. The galaxies aren't racing through a static arena like cars on a highway. The arena is changing scale, carrying them along like raisins in rising dough. Imagine dots on the surface of a balloon, but now you live on that surface. As the balloon inflates, the dots separate without crawling across the rubber. The surface itself expands. Each dot sees all the others receding. No dot is special, no dot sits at the center. Replace that two-dimensional surface with the 3 dimensions you inhabit. The expansion doesn't need an outside because outside is a notion defined by the space that's expanding. This idea bent even Einstein's intuition. He once added a term to hold the cosmos. Static, later calling it a blunder. Yet the expansion is real, and we can measure its fingerprints. How do we know it's the arena stretching and not just galaxies moving through it? Watch what expansion does to light. As a photon travels, the space it crosses grows under it. The wave crests get pulled apart. Blue arrives as red, visible arrives as infrared. Wavelengths lengthen with the universe's scale. That stretching, cosmological redshift, is not a metaphor, it's data. And it tells us the key truth that makes the paradox dissolve. The universe doesn't expand into anything. It expands by changing the ruler that measures distance everywhere at once. When the ruler changes, every separation grows, and no edge is required. Tonight, if you step outside, try swapping the balloon in a room for a grid with no boundary, silently enlarging. The grid is the thing. There is no surrounding space it has to conquer. Once you see that, the question, what does it expand into, turns into a compass pointing nowhere. It's like asking what lies north of the North Pole. The words are fine, the map you're using is not. In the next section, we follow a single beam of ancient light and watch expansion tug at it, cycle after cycle, for billions of years. The numbers will make the picture unavoidable. Imagine a lighthouse in a distant galaxy firing a steady train of light waves toward us. Each crest leaves with a fixed spacing, its wavelength. If the universe were static, those crests would arrive with the same spacing, like a metronome that never drifts. But our universe doesn't hold still. While the photon is in flight, the walkway beneath it lengthens. The distance between crests stretches because the fabric those crests traverse is stretching. By the time the light reaches our telescopes, its color has shifted redward. That shift is not a Doppler siren from motion through space. It's the footprint of space-changing scale. You can quantify this. Astronomers define redshift, Z, as how much the wavelength has been stretched. Observed equals original times 1 plus Z. If Z equals 1, the wavelength doubled. If Z equals 10, the wavelength is 11 times longer than when it left. We measure Z by reading the barcodes in starlight, thin, dark, and bright lines created by specific atoms. Those lines always appear at known lab wavelengths. When we find them shifted toward red, we know precisely how much the universe's scale has changed during the light's journey. This is more than pretty theory. Type Ia supernovae explode with near uniform peak brightness, letting us map distance from apparent dimness, while redshift tells us how much stretching happened on the way. Plot brightness against redshift, and you get a history book of expansion. That book contained a surprise in 1998. Distant supernovae were dimmer than expected. Space had expanded more during their light's travel than a decelerating universe would allow. Expansion was speeding up. Something in the vacuum, what we now call dark energy, was pushing the metric apart. But even before that discovery, redshift alone had already overturned the explosion from a center picture. If galaxies were simply flying through space, you'd expect a messier pattern. Instead, we see a clean relation. The farther the galaxy, the larger the redshift. Not because it started with a bigger shove, but because its light spent longer on an expanding road. Each crest got stretched by more cumulative growth. The pattern doesn't need a center. Any observer, anywhere, would find the same law. There's an everyday way to feel this. Picture walking an airport moving walkway that's quietly accelerating under you. Your steps are uniform, but the floor lengthens between footfalls. If you track step-to-step distance at the beginning versus near the end, you'll record a drift you didn't cause. The walkway did. In the cosmos, we detect that drift with spectra instead of shoe prints. When we line up sources at different redshifts, we also line up different eras. A galaxy at Z equals 2 comes from a universe 1/3 its present size. Z equals 10 from a universe roughly 1/11 as large. We aren't just looking far, we're looking back at smaller rulers. The same photon that began as fierce ultraviolet can arrive as infrared heat after billions of years of scale growth. This is the first hard, testable lesson of expansion. Light is the messenger, and it never lies about what space did underneath it. The universe's story is written in stretched waves. Read them carefully, and the paradox dissolves. It isn't going anywhere, it's changing everywhere. Walk outside on a clear night, and it feels like you're looking at everything. One giant dome of stars that must be the universe. But you're staring from the inside of a bubble. That bubble is not made of glass or dust or force fields, it's made of time. Light travels at a finite speed, and the universe has a finite age. Put those two together, and there's a maximum distance from which light has had time to reach you since the beginning. The age we infer from multiple, independent measurements is about 13.8 billion years. You might guess then that the horizon sits 13.8 billion light years away. Expansion says otherwise. While ancient light was en route, space kept growing beneath it. So the places that sent that light are now much farther than the naive time times speed number suggests. Today, the radius of the observable universe is about 46 billion light years. That's the size of our bubble, everything from which light has had time to arrive, given a changing ruler beneath it. Beyond that horizon, there is almost certainly more universe, likely a lot more. But we cannot see it, not because it's dim or hidden, but because its earliest messages haven't had time to get here. We live with a fog made of time. Delay. Look at the Andromeda galaxy and you peer 2.5 million years into the past. Look at the most distant known galaxies and you're looking more than 13 billion years back, when the first stars were only beginning to light up the cosmic dark. There's a sharper edge inside that horizon, the surface of last scattering, the moment roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms. Before that, space was a thick plasma that scattered light like a glowing fog. Photons couldn't travel far without getting bounced. When the fog cleared, the first long-haul photons set out. Some of them arrive at Earth today as the cosmic microwave background. That relic light is our earliest possible snapshot. We cannot see further back with light because earlier space was opaque. This horizon isn't static. With each passing second, a slightly older slab of the universe's past reaches us, and our observable bubble grows by 1 light second, adjusted by the fact that space is still expanding while those photons finish their trip. The boundary is a moving target we never quite catch. It's also deeply personal. Every observer in every galaxy lives at the center of their own observable sphere, not because they are special, but because the center simply means here, now. This is where the expanding into what question quietly fades. The bubble's edge is not a wall in space, it's a limit in time. Outside our bubble, the universe can be as rich and busy as inside. We just haven't had time to learn about it. When you imagine an edge you could fly to and touch, you're mixing up two different kinds of boundaries. Rocket engines won't help with a time horizon, only patience would. If the universe weren't stretching the road as you wait, knowing we live in a horizon changes how we think about evidence. It draws a sharp line between what can be measured and what can only be modeled. Inside the line, we can test our ideas. Outside it, we can only infer. That humility is a strength, not a weakness. The bubble doesn't make the universe small, it makes our methods honest. Turn an old television to static, and a tiny fraction of that hiss is energy from the infant universe. Not metaphorically, the cosmic microwave background is real radiation arriving from every direction, the cooled remnant of the moment the fog lifted and light could finally travel. It's the oldest light we can see, and it carries a detailed record of what space was like when it was about 1,000 times smaller than today. When that light went free, the universe's temperature hovered around 3,000 degrees Kelvin, orange-white hot, like a star's photosphere. Over billions of years, expansion stretched its wavelengths from visible and infrared down into the microwave band, cooling it to about 2.7 degrees above absolute zero. That cooling isn't the light getting tired, it's the metric growing. Every crest and trough was pulled apart by the same scale factor that stretched galaxies away from one another. When satellites like COBE, WMAP, and Planck mapped the microwave background, they found something astonishing. The glow is almost perfectly uniform, smooth to a few parts in 100,000, peppered with tiny temperature ripples. Those ripples are not random noise. They are frozen imprints of sound waves that rang through the hot plasma of the early cosmos. Where the plasma was slightly denser, gravity squeezed, pressure pushed back, oscillations formed. When the universe became transparent, the pattern of those waves was snapshotted into the light that's now washing through your room. Decode that pattern, and you learn the universe's composition and shape. The positions and heights of the acoustic peaks in the CMB's power spectrum tell us the geometry is very close to flat. That ordinary matter makes up only a small fraction of the whole, and that most of the gravitational mass is some non-luminous dark matter. They also tell us there's a uniform energy in the vacuum, dark energy, that now drives accelerated expansion. All of that is read from ripples in a sky temperature map. Just as important is what the pattern lacks. If the universe had a preferred center or a nearby edge, if it were drastically curved on observable scales, or if space had tangled topologies that forced light to wrap around and repeat, we'd expect repeating circles or obvious anisotropies in the microwave background. We don't see them. The sky looks statistically the same in every direction, consistent with a universe that is homogeneous and isotropic on the largest scales we can test. That doesn't prove infinity. It says that within our horizon, space has no built-in special places. The CMB isn't only a photo, it's a clock. Its spectrum is a near-perfect blackbody. Its temperature tells us how much the universe has cooled. Its polarization patterns whisper about how the first stars reionize the fog later on. Even the slight lensing of the CMB by intervening matter lets us map how structures grew as expansion tugged them apart and gravity gathered them back together. When people say the universe expands, the microwave background is why that claim is more than a story. It is a measurement across the whole sky in every direction, tied to a simple thermal curve that only makes sense if wavelengths were stretched as the metric grew. You're not believing in expansion, you're reading it in fossil light that never stopped traveling. And here's the twist that sets up what comes next. The very smoothness of the CMB raises a puzzle. Regions on opposite sides of the sky look nearly identical, even though there wasn't enough time for light to cross between them before the fog lifted. How did they coordinate their temperatures so precisely without causal contact? The answer points to a brief, violent chapter that occurred even earlier than this light. An episode that changed the scale of the universe more in a blink than the rest of history has managed since. The early universe presents a riddle. Opposite sides of the sky match in temperature to 1 part in 100,000. Even though under simple expansion, those regions could not have communicated before the cosmos became transparent. That's the horizon problem. There's another. The geometry of space is astonishingly close to flat. Any slight early curvature should have grown into something obvious by now, but we don't see it. That's the flatness problem. A third puzzle lurks in the background. Where did the tiny initial ripples come from that later grew into galaxies? A single idea addresses all three. Inflation proposes that a sliver of a second after the beginning, space underwent a burst of exponential growth, doubling at a staggering rate, driven by a high-energy field stuck in a temporary state. This isn't a firecracker launching matter outward, it's the yardstick changing length faster than light could cross even tiny regions. Distances that were once small enough to share a temperature got blown up beyond each other's horizons. That makes their match unsurprising. The smooth gets ironed flat. Any initial curvature is smeared away until, on our scales, it's indistinguishable from zero. And the tiny quantum jitters of the inflationary field get stretched up from subatomic scales to cosmic ones, seeding the density ripples we now map in the microwave background and the distribution of galaxies. This sounds speculative, but it leaves testable fingerprints. Inflation predicts the pattern of those microwave ripples. Should be nearly scale invariant, similar levels of clumpiness across many sizes, with slight tilts we can measure. That's what Planck finds. Inflation suggests space should appear flat within our horizon. It does, to within tight limits. Inflation implies a specific, random-looking texture rather than sharp edges or repeats. That's what we see. Some inflation models also predict a faint background of primordial gravitational waves that would twist the CMB's polarization in a distinctive way. We haven't nailed that signal yet, but experiments keep pushing. Inflation also reframes the expansion versus outside question. In an inflating phase, asking what the growth is inside of misses the point more than ever. The field's energy density acts like a temporary vacuum pressure that makes the scale factor explode in value. There is no boundary being pushed back. There is only a ruler that, for a brief epoch, lengthened everywhere faster than anything could respond. When inflation ends, the field's stored energy dumps into ordinary particles in a reheating event, and the universe continues expanding and cooling in the more familiar way. But the initial conditions are no longer arbitrary. The smoothness has a cause, the flatness has a cause, the seeds for structure have a cause. Those causes are rooted in a change in the metric, not a motion through a container. Inflation might not be the final word, and its microphysics are under active study. But as a chapter in the story of expansion, it turns a string of coincidences into a single, testable mechanism. It also opens a door to even stranger possibilities because some versions of inflation don't end everywhere at once. They end in patches, like frost forming on a window, while other regions keep inflating. That picture leads to a multiverse, not a pop culture wish machine, but a natural byproduct of how fields can behave in quantum settings. Whether that's our reality or not, the logic still circles back to the same lesson. Expansion is a property of the metric itself. It needs no outside to press against. For most of cosmic history, gravity fought expansion to a draw that slowly favored growth. Matter thinned as space enlarged, and the overall pull weakened with time. It seemed natural to expect the expansion to keep slowing, maybe even reverse in some far future. Then we measured supernovae at great distance and found the opposite. The expansion is speeding up. The cosmic ruler isn't just lengthening, it's doing so at an increasing rate. The cause we bundle under a spare name, dark energy. It isn't dark because it's shadowy, and it isn't energy in the household sense. It's a uniform energy density associated with empty space itself, a pressure with the strange property of making gravity act repulsively on the largest scales. If that sounds like Einstein's old cosmological constant, it is. He introduced a term with the same mathematical behavior to hold a static universe in place, then threw it away when expansion was discovered. The universe brought it back, not to freeze growth, but to accelerate it. Here's the oddity that sets dark energy apart from matter. If you double the size of a box, the density of air inside drops by half. Spread the same number of atoms across twice the volume and you dilute them. But if dark energy is a true cosmological constant, its density stays the same as space grows. Double the volume and you get twice as much dark energy. In the equations, that behavior makes the scale factor curve upward. Eventually, it dominates the ledger because matter keeps thinning while vacuum energy doesn't. Observations of the cosmic microwave background, galaxy clustering, and supernovae all point to a simple budget today. About 5% ordinary matter, about 27% dark matter, and the rest, about 68% dark energy. If it remains constant, the future is a slow fade into a cold, empty state. Structures bound by gravity, galaxies and clusters, stay together. But unbound galaxies cross our horizon and wink away, not by exploding, but by receding so fast that their light can never catch up. The night sky of the far future will hold only the remnant of our local group, merged into a solitary elliptical galaxy adrift in darkness. The cosmic microwave background will redshift into wavelengths impossibly long to detect. The evidence we enjoy today will slip out of reach. There are stranger possibilities. If dark energy isn't a constant, but a dynamic field that grows stronger with time, acceleration could ramp up until it tears apart galaxies, solar systems, molecules, even nuclei, a scenario called the Big Rip. If instead it weakens or becomes negative, gravity could retake the lane and halt the expansion, even reverse it. Present data favor the constant case, but the door isn't locked. Either way, the lesson for our core question doesn't change. The acceleration is not a shove from outside, it's a property of the vacuum inside, a term in the equations that tells the ruler how fast to grow. Dark energy also clarifies what critical density means. There's a particular energy density that separates universes that recollapse from those that expand forever. We measure a total very close to that value once we include dark energy's contribution to the geometry. That near balance isn't an accident in modern models. Inflation naturally flattens space toward the critical case. Again, metric-first thinking cleans up the paradox. Expansion is not a thing moving, it's a relationship changing. Ask what the universe is expanding into, and you've already pictured a shape with an outside, like a growing sphere in a room. Geometry gives you a way out of that trap. In general relativity, space can be flat, like a tabletop, positively curved like a sphere's surface, or negatively curved like a saddle. Locally, all three can look the same to small creatures. Globally, they behave differently. On a sphere, straight lines meet again. Triangles have angles that add to more than 180 degrees. On a saddle, lines diverge. Triangles sum to less. Measurements of the microwave background and galaxy surveys show that within our horizon, space is very close to flat. But flat doesn't necessarily mean infinite, and it doesn't imply an outside even if it were finite. You can take a flat sheet of paper and identify its opposite edges so that moving off one side brings you back on the other. That wrapping turns a flat geometry into a finite topology without needing a surrounding room. In 3 dimensions, there are analogous wraparound spaces, compact but edgeless. Fly straight long enough and you'd return to your starting point without ever crossing a border. No edge, no beyond. Just a geometry that closes on itself. If our space were small and wrapped that way on scales comparable to our horizon, we might see matching circles in the microwave background where light has taken different wraparound routes to reach us, or repeated patterns of distant structures. Astronomers have searched for those signatures and found none so far. The simplest reading is that if space wraps, it does so on scales far larger than we can see. The sky looks statistically uniform in every direction, which is what you expect if there's no special edge lurking nearby. Even in an infinite flat case, the into what question misfires. Infinity doesn't need a container. Think of an endless grid. You can double the spacing between grid lines everywhere and still have no boundary. Distances grow, no outside appears. Expansion is the change in spacing, not the grid drifting through a bigger room. Curvature also changes how you imagine time. Space and time are woven together. You don't stretch one without touching the other. In the early universe, when the scale factor was small, clocks ticked in a denser, hotter environment. As the ruler lengthens, not only do distances change, the way different observers slice now across the cosmos changes too. There is no universal present that everyone shares. When you ask what the universe is doing right now, you've smuggled in a global clock that relativity doesn't give you. That's a clue that some everyday questions aren't wrong so much as undefined. The upshot is disarmingly simple. You don't need an outside if your geometry supplies no edge, and our best observations show no edge within view. Whether space is infinite or wraps on scales far beyond our horizon, the expansion we see is the ruler changing, not a surface pushing into a larger void. When you stop looking for walls, the question you started with dissolves and a better one takes its place. How exactly does the ruler change and why? Expansion sounds like it should smear everything into mush. Yet when you look at deep images of the sky, you see filaments, clusters, and grand spirals. If space is stretching, why doesn't the universe just dissolve? The answer is that two processes run at once on different scales. The global metric grows everywhere, but gravity is local and relentless. Where there is a tiny excess of matter, gravity magnifies that excess. Where there is a tiny deficit, gravity deepens the gap. The expansion sets the stage, gravity writes the plot. Those initial tiny differences came straight out of the early universe. Inflation took quantum jitters and stretched them into gentle hills and valleys in density. After the plasma cooled and atoms formed, light decoupled, and the pressure that held the plasma smooth relaxed. Gravity took over. Regions slightly denser than average pulled in more matter and grew denser still. Regions slightly thinner gave up material and grew emptier. That feedback builds the cosmic web, sheets, filaments, and nodes threaded across billions of light years with vast voids in between. This isn't a tug of war that expansion always wins. Think of it as a speed comparison. Expansion carries unbound regions apart at a rate set by the scale factor's growth. Gravity gathers bound regions together at a rate set by their own mass and size. If a clump becomes dense enough that its self-gravity beats the local stretch, it peels off from the flow. Galaxies condense inside dark matter halos. Clusters condense from collections of halos. Inside those, stars form as gas cools and collapses within clouds where electromagnetic forces and chemistry take the baton from gravity. That's why the space between clusters behaves one way and the space inside a galaxy behaves another. Expansion tries to pull at everything, but inside gravitationally bound systems, the forces that hold things together are stronger than the gentle global drift. The Milky Way doesn't swell with the Hubble flow. Your body doesn't elongate with the cosmic scale factor. The atoms in your screen don't notice any of it. Local bonds beat global stretch by an absurd margin in everyday life. Over long times, though, the balance shifts. As dark energy drives acceleration, unbound regions grow farther apart faster. Fewer new clusters will form. Existing clusters will keep their members, but their neighbors will drift beyond reliable contact. The web's largest threads go taut and thin. Meanwhile, inside the islands that remain, the story runs on for a very long time. Stars burn, die, and recycle material into new stars until fuel runs out. Expansion and gravity coexist because they work on different scales with different rules. The metric grows, within it, pockets resist. Both facts are true at once, and none of this needs an outside. The growth that spreads the web and the pull that knots it happen in the same self-contained fabric. The universe expands by changing scale. And within that changing scale, structure thrives as long as gravity has matter to gather. Knowing the universe expands is one thing, putting numbers on it is another. You can't stretch a tape measure across 1 billion light years, so astronomers build a ladder, each rung calibrating the next, until the units reach the depths where expansion writes its signature. The point isn't to pile up complexity, it's to make sure every step rests on something you can test. The bottom rung is geometry you can see from your backyard. As Earth orbits the sun, nearby stars trace tiny ellipses against the distant background. That shift is parallax, and it gives you direct distances to stars within hundreds or thousands of light years. With those distances in hand, you can look for stars whose intrinsic brightness links to something you can measure easily. Cepheid variable stars fit the bill. Their pulsation period tells you their absolute luminosity. Compare that true brightness to how bright they look and you get their distance, now out to neighboring galaxies. Next come standard candles that burn far brighter and can be seen across billions of light years. type II supernovae explode with a near-uniform peak brightness because of how their progenitors reach a critical mass. Calibrate them with Cepheids in the galaxies where both appear, and you've built a bridge from nearby space to the deep universe. With supernova distances, you can now plot how far a galaxy is against how stretched its light is. That plot is where acceleration showed itself. Candles aren't the only trick. There are standard rulers too. The early universe's sound waves left a preferred scale in the distribution of galaxies today: baryon acoustic oscillations. Measure that built-in yardstick across different redshifts, and you get snapshots of the scale factor at different times. There's also gravitational lensing, in which massive structures bend light and reveal their mass directly, tying growth of structure to the expansion history. Every rung comes with uncertainties and biases that teams spend years beating down. Dust reddens light. Supernovae aren't perfectly identical. Cepheids live in environments that can tweak their behavior. That's why multiple independent methods matter. When they converge, confidence rises. When they disagree, you learn something new about errors or about physics. All those measurements feed into a single curve, the scale factor as a function of time. Fit that curve and you can ask precise questions. How much matter is there? How flat is space? How strong is dark energy, and does it change? The latter doesn't answer into what, because the question still doesn't apply. What it does is turn the hand-waving into numbers, and the numbers into a story you can test again tomorrow. Plot distance against redshift for many galaxies, and you find a straight line near home. Farther means faster receding. That relation is Hubble's law, and the slope of that line today is the Hubble constant. It tells you how fast space expands per unit distance right now. Simple in concept, hard in practice. Different ways of measuring that slope give numbers that don't quite agree. That mismatch is the Hubble tension. One path measures the local universe. Build the ladder. Parallax to Cepheids to supernovae to far galaxies. Fit the line near the present. You get a number that hovers in the low 70s when expressed in the usual units. The other path looks not at nearby candles, but at ancient ripples. The microwave background's detail pattern depends on the entire expansion history from the early universe to today. Fit a model to that and evolve it forward. That approach gives a number in the high 60s. The gap is only a few percent, but the error bars have shrunk enough that it's not easily waved away. Either there are subtle systematics lurking in one or both methods, or the model that links early and late times is missing a piece. Hidden biases can do a lot of damage. Perhaps supernovae evolve slightly with environment. Perhaps Cepheid calibrations hide metallicity effects. Perhaps parallax baselines carry tiny system errors. Teams keep cross-checking and refining to make sure the rungs are sound. If the rungs hold and the numbers still disagree, the simplest model of the universe may need an adjustment. Maybe there was a brief pulse of extra energy density in the early universe, such as an additional light particle species or an episode that tweaked the sound horizon. Maybe dark energy isn't perfectly constant and changes in a way that reconciles early and late measures. Maybe gravity itself needs a tiny correction on cosmological scales. None of these options are adopted lightly. Each has consequences that show up in other data, and those cross-checks are unforgiving. The tension doesn't change the core lesson of expansion. It sharpens it. The universe isn't coy about stretching, light tells you so. The tension lives in the fine print about exactly how fast the ruler grew at different times. Working out that detail isn't just bookkeeping. It is how science turns a broad picture into a precise one. When good numbers don't match, the right response isn't to pick a favorite. It's to ask better questions and build better measurements until the story clicks into a single, coherent curve. If space keeps making more room, where does the energy come from? The first instinct is to appeal to conservation. Energy can't be created or destroyed, so how can there be more vacuum energy in a larger volume than before? The trick is that in general relativity, energy accounting isn't as simple as a fixed piggy bank. Gravity contributes negative energy, and the bookkeeping happens in the geometry, not in a global cash register. Imagine a universe with dark energy that behaves like a cosmological constant. Its density stays the same as the scale factor grows, so the total amount in any co-moving volume increases as the volume increases. That sounds like cheating. But as matter spreads out, the gravitational binding energy of that matter becomes less negative. Time is up. The change in negative gravitational energy balances the positive increase in vacuum energy. The sum can stay steady even while the parts change. There's another important nuance. In a curved, expanding spacetime, total energy of the universe isn't a well-defined quantity the way it is in a box with walls and a stopwatch. No one can point to a single number and watch it tick with time for the whole cosmos. Conservation still holds locally. In small regions where spacetime is nearly flat, energy and momentum are conserved in the usual way. Globally, what's conserved is encoded in the Einstein equations, which tie how matter and energy curve spacetime to how the metric evolves. This isn't a loophole invented to save appearances. It's a direct consequence of how gravity works when geometry isn't a backdrop but a participant. Treat the metric as dynamical, and the old box-based intuitions loosen. The universe doesn't violate conservation by expanding. It obeys a deeper rule where energy and geometry pay each other back. Seen this way, space creating itself is just a phrase for the scale factor increasing while the stress energy content and the curvature evolve together in a consistent ledger. Nothing has to pour in from outside. There is no outside. There is a field equation that says, given this content, the ruler changes like that. And given that change, the content dilutes, heats, cools, and redshifts in this way. It is internally complete. If this still feels slippery, that's fair. We're trained on systems with walls and clocks where energy balances are easy to write down. The universe offers no walls and no universal clock. The right cure for the discomfort isn't to add an imaginary container beyond the sky. It's to learn the accounting the universe actually uses. Stand anywhere on the surface of a perfect sphere and it feels like the top. Every direction slopes away evenly. In an expanding universe that is homogeneous and isotropic on large scales, every observer measures the same pattern. Galaxies recede, and the recession speed grows with distance. That universal pattern can trick you into thinking you sit at the center of a blast. You don't. There is no center because there is no preferred point. The balloon analogy, handled carefully, helps. Draw dots on the surface and inflate it. Each dot sees the others recede, and the ones farther away recede faster. But try to pick the center on the surface and you won't find one. The true geometric center lives in a dimension you, as a surface dweller, don't inhabit. In our case, there is no evidence we need an extra dimension to host a center. The expansion we measure is intrinsic. The metric grows without pointing to any special place in three-dimensional space. This is built into the equations. The simplest solutions to Einstein's field equations that match a universe like ours are the Friedmann, Lemaitre, Robertson, Walker models. They assume homogeneity and isotropy on large scales, which means every location and every direction are statistically the same. There can be local lopsidedness, clusters here, voids there, but averaged over hundreds of millions of light years, the pattern smooths out. That's exactly what galaxy surveys and the microwave background maps reveal. The centerless nature of expansion has practical consequences. Every galaxy lives at the center of its own observable sphere. Every sphere is finite because time is finite, not because space ends. Ask where did the Big Bang happen, and the best answer is everywhere. At early times, the scale factor was small everywhere, and the temperature was high everywhere. What later became the patch of space you now occupy was once hot and dense, just like every other moving patch. There was no single point you could mark as the origin and fly to. Losing the need for a center also dissolves a common worry. If the universe has no preferred point, how can we define motion at all? Locally, motion is defined just as always, by how things move relative to their neighbors. Globally, the Hubble flow gives you a natural rest frame in which the microwave background looks the same in every direction. Our solar system moves slightly through that frame. We detect a tiny dipole in the CMB because of that motion. But that frame isn't a throne at the middle. It's just the most convenient way to slice the big picture. When you stop searching for a central balcony seat, the view gets simpler. Expansion is a change in scale that every place experiences equally on large scales. No edge, no center, no outside. Just a fabric whose ruler lengthens and a sky that records it. You can have a world with no edges and still keep it finite. Wrap the left edge of a square to the right and the top to the bottom, and you've made a torus, a donut surface. Walk straight long enough and you eventually return to your starting point without ever stepping over a border. Locally, it feels flat. Globally, it closes on itself. No outside is required. Extend that idea to 3 dimensions and you get a variety of possible wraparound spaces. The geometry can remain nearly flat while the topology loops. If our universe had that sort of compact topology on scales near our horizon, we'd expect to see signatures, repeated circles in the microwave background where light travels around the cosmos and meets itself from different directions, or multiple images of the same distant structures appearing in separated patches of sky. Astronomers have looked hard for those patterns and so far found none. That nudges us toward one of 2 conclusions. Either space is truly infinite and flat on large scales, or it's finite and wrapped, but the wrap size is much larger than the part we can see. Both possibilities kill the need for an into. An infinite flat space can have its scale multiplied without revealing an outer region. A compact wrapped space grows by increasing its internal size parameter without expanding into anything external. In both cases, expansion is a change in spacing, not a motion through a surrounding medium. If infinity makes you uneasy, you're not alone. An infinite universe raises deep questions about repetition and probability. With finite ingredients and endless volume, configurations repeat somewhere. That's philosophy pulling at cosmology's sleeve, not cosmology making a claim beyond what the data can support. The observations tell you about curvature and topology within your horizon. They don't certify infinity. They certify that if there is an edge or a small wrap, it lies beyond what light has had time to show us. There's a further twist. Space and time come as a package. The way you glue space to itself can depend on how you slice time. In relativity, different observers cut space-time into space plus time differently. That means the intuitive picture of a static shape being scaled up is, at best, a snapshot. The real object is the entire evolving space-time. Expansion is baked into that object's geometry. You don't need a room to put it in. You need a map that respects what it is, a 4-dimensional shape whose size parameter changes as part of its definition. The donut is a tool, not a claim. Its value is to break the habit of imagining walls beyond the stars. Once you've trained that reflex out of your thinking, the original question stops being a puzzle and starts sounding like a category mistake. Space can grow because growth means multiply the internal distances, not push into somewhere else. Sometimes the balloon analogy tempts people to import a real higher dimension. Maybe our 3-dimensional space is like the balloon's 2-dimensional surface, embedded in a larger arena. In some speculative models, that's more than a metaphor. Certain versions of string theory and brain cosmology picture our universe as a 3-dimensional membrane floating in a higher dimensional space, with matter and light stuck on the membrane while gravity can leak into the bulk. If a scenario like that were true, then in a literal sense, our space would exist inside a larger space. Would that mean the universe expands into the bulk? Not necessarily. Even in brain models, the expansion relevant to us is still the change in our membrane's scale factor, a property of the membrane's own geometry. The bulk provides context, not a destination. The key measurements we make, the redshift of light, the smoothness and ripples of the microwave background, the growth of structure, still read the scale change on the membrane. Do we have evidence for extra dimensions? Not at present. Particle colliders have looked for missing energy signatures that might hint at gravitons slipping into hidden directions and found none so far. Precision tests of gravity at short distances show no deviation from the inverse square law down to sub-millimeter scales. Cosmological data fit well without invoking extra dimensions. That doesn't kill the idea, it sets hard constraints on how any extra dimensions could behave. It's important to separate 2 different uses of outside. One is a teaching image that lets you picture intrinsic expansion with a familiar embedded surface. The other is a claim about fundamental architecture. The first is a crutch you can discard once the concept lands. The second is a hypothesis you test against data. If someday evidence points to higher dimensions, the everyday implications would still look like what we've described. Wavelengths stretch, horizons exist, structures grow and thin, and the metric changes. The presence of a bulk wouldn't rescue the old question. Expansion still wouldn't need a beyond to push into. because the expansion you measure is intrinsic to the object you live in. So you can enjoy the picture of parallel membranes in higher spaces as a playground for ideas. But the universe you can test already provides a complete answer. The scale factor grows, the ruler changes. No outside is required to make that sentence true. Expansion doesn't just stretch distances, it stretches the way we compare clocks across the cosmos. Watch a supernova in a galaxy with high redshift, and you'll see its rise and decline play out in slow motion compared to the same kind of event nearby. That time dilation isn't caused by the star exploding lazily, it's the scale factor at work. The space that the light traverses grows during the trip, and the intervals between the wave crests that carry the event's timing get lengthened. When those crests arrive, the entire light curve is stretched by the same factor as the wavelength. This leads to a subtle but important point. There is no universal now slicing the universe into simultaneous snapshots. In relativity, simultaneity depends on your state of motion and the path you take through space-time. In cosmology, we often use a convenient time coordinate tied to the average motion of galaxies, in which the microwave background looks the same in all directions. That coordinate gives a clean way to talk about the age of the universe and draw pictures where the scale factor marches along a single axis. But it's a choice that simplifies the math, not a cosmic clock nailed to the wall. As expansion accelerates, these timing effects grow more extreme for very distant sources. Events at the edge of our observable universe look frozen, stretched toward infinity, as their light struggles against the growing gulf. We are not watching them in real time. We are watching them as they were when the scale factor was tiny and the ruler short. This has consequences for how we imagine the past and future. When you look out, you look back. The farther you look, the younger the universe you see. That means your mental picture of the universe at once doesn't exist the way a map in a textbook does. Replace the flat diagram with a film strip that mixes frames from different eras, each distorted by the growth that happened during the light's travel. The stretching of time also softens the urge to ask what the universe is doing right now everywhere. That question asks for a global slice that nature doesn't privilege. The better questions follow the data's own structure. What did this galaxy do when the scale factor was half today's value? How does the pattern of stretched light from that era fit the story we read in the microwave background? If your questions match the way information arrives, your answers stay anchored. When you accept that time and distance stretched together, the expansion stops being a trick and starts being a tool. You can read ages, speeds, and scales directly from the light curves and spectra of things that happened long ago. The ruler isn't just moving, it's labeled, and the labels are legible. Given what we see today, where's the expansion likely headed? If dark energy is a cosmological constant, acceleration continues forever. Structures that are already bound, galaxies, clusters, remain intact, but unbound neighbors drift beyond each other's horizons. Star formation dwindles as fresh gas is used up or heated. The bright era gives way to a long twilight in which new stars are rare and old stars fade. Over far longer spans, only remnants remain: white dwarfs, neutron stars, and black holes. Those too have clocks. Black holes evaporate through Hawking radiation on timescales so long they make the current age of the universe look like a blink. Eventually, even they go dark. What's left is dilute radiation, and lone particles spread thin across an ever larger volume. That is heat death. No temperature differences to drive processes, no gradients to extract work, no new complexity born from gravity's tug. That is the quiet ending. A louder one is possible if dark energy strengthens with time. In that case, the acceleration grows so fierce that it overcomes not just the feeble pull across clusters, but the gravity inside galaxies, then the binding of solar systems, then the forces that hold molecules together, and finally the forces that hold nuclei together. The timeline accelerates toward a singular end called the Big Rip, in which the very notion of a distance breaks down. Current data don't demand this outcome, but they can't eliminate every version of it. It remains a warning label on the bottle. If the vacuum's pressure changes the wrong way, the story ends with a snap instead of a sigh. There's a third class of endings if dark energy fades or reverses sign. Expansion could slow, stop, and reverse, heading toward a big crunch. Some models even cycle, with bounces that lead to new expansions after contractions. Evidence today favors ongoing acceleration, not reversal, but the only honest stance is conditional. We infer the future from the past and present, and we keep measuring. What endures across all these scenarios is the logic that got us here. The future doesn't need an outside to host it. If the expansion goes on forever, the metric will keep growing and horizons will keep shrinking what any one observer can see. If a rip arrives, the metric will blow up in finite time. If a crunch awaits, the metric will head back down. In every case, the question into what adds nothing. The ruler changes, the film runs. The ending depends on the parameters, not on a container. There is one more kind of endurance that matters. Meaning doesn't require permanence. The universe does not promise to keep the evidence available forever. It offered it to us now. We read it. We built a story that fits the light. That by itself is a rare alignment. By now, the phrase should feel different in your mouth. The universe isn't expanding into nothing because into presumes a place to go. Expansion is not motion across a larger room. It is the room changing scale. The distances between unbound things grow because the metric grows. Light remembers that change. By arriving stretched, horizons exist because time is finite, not because walls stand at the edge of space. Gravity builds islands that ignore the tide. Dark energy bends the curve of the future without pushing from outside. This shift in language isn't pedantry. It is the difference between a bad question and a useful one. Ask what the universe expands into and you'll chase a ghost. Ask how and why the scale factor changes and you'll climb a ladder of measurements that starts with the parallax of nearby stars and ends with ripples in ancient light. Along the way, you'll meet a handful of big ideas that hold up under pressure. Space can be flat, curved, or wrapped without needing a beyond. Smoothness on the largest scales coexists with fractal-like structure on smaller ones. Time does not slice neatly across all of space. Energy accounting in a dynamical geometry looks alien at first and then becomes second nature. None of this demands comfort. It asks for clarity. The universe is under no obligation to mirror our household intuitions. In daily life, growth needs an outside. In cosmology, growth means multiply the internal distances and redraw the map with a larger scale bar. That's why the balloon is a teaching prop and not a claim about higher rooms. Use it, then discard it. There's also a human thread running through the math. Every time you look up, you're seeing a limited film reel cut by the speed of light and the age of the cosmos. Beyond your horizon, the story goes on. You don't need to know how it all ends to know what the light says now. It says the metric grew. It says the early universe was smooth with tiny ripples. It says vacuum has a pressure that leans the future toward emptiness. It says gravity can make islands in a rising tide. If you want a sentence to carry out of this series, take this one. The universe expands by becoming more universe. Not by entering a space that was waiting for it, but by changing the size of the space that already is. That is a precise statement with measurements behind it. If it feels like philosophy, that's only because our language took time to catch up to our instruments. Now it's your turn to teach the idea forward. Try explaining it without the word into. Try using light stretched color as your anchor. Try telling someone that their center is as good as any center because there are no special seats. If the paradox doesn't vanish, it at least loses the power to stall you, and that's enough. The sky hasn't changed. Your questions did.